So good afternoon to all of you. Myself, Anil Kumar, and I hope you are able to see me in the screen as a pop-up screen. And I hope you are able to listen my voice. You can text me if you are able to listen my voice, or if you are not able to listen my voice. Okay, Mauritius, yes, both are okay. Thank you, Mrs. There was somebody from Mauritius. It's audible, sir. Okay, it is Pramod K. Toyloku from Mauritius. And Mrs. Malika Rosie. Okay, fine, thank you. So we'll start quickly. So the topic, if you see today, for me, there are two topics. The first topic which I'm covering today is image classification techniques. So in this, you have already gone through with basic topics and little further image processing techniques. But again, I will try to reconnect what is image, and then we will see what do you mean by classification techniques. So myself, Anil Kumar, and I'm looking as a head of photogrammetry and remote sensing department, where Dr. Meenakshi Kumar is there as a coordinator for you all from different countries. I can see Azerbaijan, Mauritius, different people are present. Thank you for joining. So my topic today, I will cover in this separability analysis mainly. Then I will go for image classification and then accuracy assessment. So these are the three subtopics I will try to cover. If not, I can keep it for tomorrow. But my motive will be that you people try to understand these topics. But before this, I will try to cover the basics of image, try to understand what is image. You may be knowing it, but let me just refresh and try to reconnect and think what is actually image. So this can be an image like a rose, a beautiful rose, one more, and this is so cute, a baby, right? Maybe just few months. And of course, this one. These are all images you accept, but I don't see these images as we are seeing on the screen. We'll see further more images. So here you can see this is a remote sensing image, and this can be a sea area, and this is the land area. If I try to zoom and try to see small area, the image looks like this, like a chessboard, right? Some black and white boxes. And if I see further, actually image is basically numbers. So once you go on zooming it, you found the image is nothing. Image is basically numbers. Image is not like baby, rose, whatever we are seeing previously. So that is not image actually, because once you go inside your body, you see soul, what we talk about soul. So that is the main thing. Like in a computer, software is the main thing which is running the computer for different processing. So same way in the image, these numbers are the main thing which is there in the image. If you zoom it, you see the numbers at these squares, and these squares are called pixels. So these are called a pixel, and the pixel has number that is called digital number. So the digital number gives like a reflectance or emittance or any other information. But in the remote sensing image, these are digital numbers, can be reflectance or emittance. Further, you have seen images just now. I've shown you the rose image, baby image, or remote sensing image. That is one way to see the image, and there we are using maximum 3 bands to see the image. Why 3 bands, not more than 3? Because on the display screen, like a computer, and on the monitor of the computer, we have three colors, three primary colors: red, blue, and then here green, and then you have here red. So this is green. So you have three guns, so you can pass each band to each gun, and then you can see maximum 3 bands to visualize your ground. But there are some other methods. This is called feature space. So here what we have done, there are 3 axes, your x-axis, and this is your y-axis, and this is your z-axis. So you can have 3-dimensional axis. So on each axis, if you plot each band, so then you can see pixels like dots, and this area where we are plotting, is called feature space. So that is a space, it is a feature, and these bands are called feature. In the literature, if you read, this band means feature, dimensionality of the data, and the space is the area where we are plotting these pixels. And these dots, if you connect with the origin, that is called feature vector. So this is your feature vector. So here you can see if it is a 2-dimensional feature. So if you plot 1 pixel, so this is your feature vector, this one. So for each pixel, you can have 1 feature vector, and this is your feature space where you're plotting all the pixels. So here you can see the pink one can be 1 class of the image, maybe the 1 object, blue one, 2nd object of the image, green one, 3rd object, red one, 4th object, and yellow one, 5th object. So here this is the one method, and this is more technical, more scientific. We can see the 2 classes are overlapping or separate. You can see here green and red is separate, but blue and pink, they are, some pixels are overlapping here. So there is spectral overlap. So this we can see in the feature space very carefully, that there is spectral overlap or not, or what is the spectral profile. So coming to separability analysis, the separability analysis we do to find out suitable bands in my given image. So quantitatively, we can select which subset of bands, that is called, or features, provides the greatest degree of statistical separability between classes. For example, we may have, suppose here 6 bands, 1, 2, 3, 4, 5, 6. So I have image of 6 bands, but all the 6 bands may not be useful. I can find out if I have to extract 4 classes. So I can find out to extract or to map these 4 classes. Do I require all the 6 bands, or 5 bands, or 4 bands, or 3 bands? Maybe 3 bands are sufficient to separate and map the 4 classes which I'm looking for. So how to know that which are the 3 bands which are sufficient out of these 6 bands of the given image? So that the answer we can get from separability analysis. So here you can see quantitatively it can tell subset of bands. Subset means if there are 6 bands out of 6, which are the 3 bands which may be sufficient to map 4 classes which I'm looking to map in the given image. So that is the main application, and we can do it in the any existing image processing software. What this separability analysis required, this requires the training data, right, or signature data of each class. So if I'm mapping 4 classes, I should have for each class training data. So using this training data, we can do separability analysis and find out which are the suitable bands to map these 4 classes. So it is basically a discrimination technique that allowed separation of the major land cover categories within a minimum number of minimum of error and minimum number of bands. So here with this technique we can find out what are the minimum number of bands required in a given image to map the classes which I'm looking for. So the requirement, as I mentioned, if training data for each class from each band are normally distributed. So one more condition this asks, that if you check for each class, if you plot, the data should be like this. If you plot the data, the training data for each class should be normal distributed, then it is possible to use these methods. So under separability analysis, there are few mathematically representing methods which can be used to find out the suitable band. So first one is the transformed divergence. So this is called in short TD. In the books also you can read, it is called TD, transformed divergence. Then second one is Jeffrey-Matsushita distance. Second one is Jeffrey-Matsushita distance. So here if you see first one, we can find out the suitable bands through graphical method. But in the graphical method, we can plot the bands as 2-dimensional or maximum 3-dimensional, and then we can see how much is the separation between the, suppose these are 2 classes, cross 1 and 2. If the separation is fine, so we can say this is band 1, band 2, band 3. Graphically, we have to see with the naked eyes that how much separation is there and that separation is acceptable or not. But here the limitation is we can plot a maximum 3 axes. Physically, we cannot plot more than three bands. So that is the limitation of graphical method. If we have only 3 bands or 2 bands, we can do that. If there are 4 bands, then it is not possible to go up to 4 bands and seeing what is the separation between 2 or more than 2 classes. But we can go for mathematical methods, expressions. First one, transform divergence. So here, if you see the statistical method with the transform divergence, it uses mean parameter as well as covariance matrix. So these are the 2 parameters we can generate from the training data of each class, and we can find out the transform divergence between 2 class or more than 2 class using this formula. So here V is the variance covariance, and M is the mean for a given class. C is the class. Here D is also class, but V is the variance covariance and D is the mean. So here you can see V is covariance and the mean, M is the mean. So from this we can find out divergence, and from here divergence we can use it here. So here it talks about transform divergence is equal to 2000 multiplied by, in the brackets, 1 minus exponential, that is E, basically this is E to the power minus DIVR divided by 8. So like this we can find out transform divergence, and if we see its value comes in this range. If it is maximum 2000, then it's called excellent class separation. If it is above 1900, then it is good separation. If it is below 1700, then it is poor separation. So when we are doing separability analysis, we have to see the separation should be 1900 or above 1900, then it is a very good separation. If it is below 1700, then it is poor separation. You can see more mathematical details on these on Jensen book. There is one Jensen book on digital image processing. So you can see more details in this book. A second one, if we talk about mathematically expression, what we have, the algorithm is called Jeffreys-Matsushita distance equation. So again, this data should be Gaussian, that is normal distribution. The data should be normal distribution like this. Removal of least effective features, so it can remove the least effective features, the bands or features which are not contributing much information, they will be removed, and transform the pixel vector into a new set of coordinates in which least effective bands are removed. So here it calculates this variable called BHAT, again using mean parameter of each class and covariance parameter of each class, and using this BHAT parameter in this expression, in this equation, we can find out Jeffrey-Matsushita distance is equal to under root 1 minus under root 2 into 1 minus e to the power minus BHAT. So like that, we can get the Jeffrey-Matsushita value. Is it okay? Some doubt, or we can take the doubts later. If some issues are there, please type in the chat box so that I can understand. People are not sleeping, they are listening. There is no issue while seeing my slides. I hope I am not moving little fast. I have little fast speed, but let me listen from you. Please type. Okay, the Mauritius Malika, Miss Malika Ruzi. No, it's okay, sir. I'm well present. Pramod K. I am well present, sir. Okay, you are present, fine. Any other from Azerbaijan and other people who are there from other countries? If you can type and type in the common group so that everybody can read. All clear, sir. Dawa Ram Singhdam Dun in from Bhutan. Then Ishak Tuna from Kenya. Okay, fine. Well understood, sir. You are clear as well. Zambia, it is okay, sir. Okay, Mose Mutambala. I'm trying to pronounce your names, which are difficult for me. No problem. I will try to pronounce your name as much clear as possible. So we'll move further. Digital. So now from Kenya, very present, sir. Okay. Line. So here I'm talking about now digital image classification. So just I talked about separability analysis. You can find out the least optimum bands using signature data of different classes you are trying to map, and find out the minimum number of bands or optimum number of bands required. So next talking about digital image classification, the objective of these operations is to replace. Here basically there is a digital word. That means we are doing this on a computer using some algorithm. We can do visual also. We can have a hard copy paper print of the image, and here we can do tracing of river, forest, and then built up area, agricultural land. Visually we can trace, but that is time consuming and difficult to edit once we trace it. But once we do digitally, it is in minimum time we can do, and we can process large number of area. So here the objective of digital image classification is that these operations is to replace visual analysis. Visual means while doing with the eyes, naked eyes, doing visual interpretation, so that can be replaced, and this can have a quantitative techniques for automating the identification of features in a scene. There is a heavy rain going on, and let me close my office window, which is water is flashing out in my room. Yeah, it's now better. Yeah, it's a rainy season going on, and today from last day it is heavy rain going on. Anyway, no problem. Let me just continue. So here you can see that I'm showing you a 5-band image, and I told you image is not like rose or baby or whatever you take pictures from your mobile phone. That may be looking for beautification of memories, but when I talk about, or when you think about processing, so you have to think images like this. Image is not like rose or baby or your own personal photographs from Kenya or from Mauritius. You are taking it from the good tourist places, but image is the arrangement of numbers in the form of row and column. So here you don't see the different objects. Basically, they are numbers. Here it is 5-band. So if you do processing, then what we are doing, we are trying to get the classification, grouping the similar pixels. So here you can see the water is labeled as 1. Then vegetation is labeled as 2 in green color, and wetland is labeled as pink, and the soil is labeled as yellow, orange color. So here grouping has been done, and the original DN value has been replaced, and now it is single band, it is single layer, right? So this is the output you get. Now coming to some classifiers which we can use, mathematical algorithms, and these algorithms are called pixel based. Pixel based means, if I talk about as a layman or a human being context, how we try to identify the object. We try to identify the object with respect to its color, shape, size. If it is a human being, we try to see its language and so forth. So we used all these parameters, but here I told you one parameter is color. So we try to identify the objects with respect to color. Also on the image, we use this color at the very for coarser images or for medium coarser images. But the color is very deep information. But if the image is very coarse, say 30 meter, 20 meter, 10 meter, so color is more dominating than other parameters like texture or shape. So if we are, color means we are using only pixel value of each pixel on the given image. We are trying to use these pixels and we are trying to classify our image. So then it is called pixel based. Parametric. So parametric means, again a very layman term, if I talk about velocity, right? So velocity we write distance covered by time. Speed is equal to distance by time. So here you calculate use this formula in India or Kenya for different cars or train or aircraft. The formula remains same, right? It does not change. But if you use this type of formulas for water flow in a river or in a canal, so you cannot use the same formula. You have to use some coefficient C. So the coefficient C for a canal water speed may be different in India, may be different in Kenya, may be different in Mauritius. So the C has to be optimized. So if you don't use C, that means for a given data, the algorithm behaves same. The data can be different, but the algorithm behaves with the same way. So then it is called parametric. But if the algorithm is not behaving same, you have to optimize every time, then it's called non-parametric. So here I'm talking about pixel-based parametric classifiers. And then I will be talking about some more categories of classification. One of the categories, unsupervised classification. So unsupervised, you can understand like in a school. In a school, there is a class and students are attending the class, like you are attending the class with me. So between you and me, you are students and I am teacher. So this class, which is going as an online mode and covering different countries, that's the beauty of it. While sitting in your home, you can connect with the different countries and different cities. So here in this class, it is supervised because teacher is present with the student. So this is the learning with the students is going as supervised learning. But if teacher is not there, teacher comes for a minute and gives some questions and asks the students to do, then the class is unsupervised. So here, same way, unsupervised classification means when we are not providing any prior knowledge, we are not providing any ground truth information to the classifier, then it is called unsupervised classification. So in unsupervised, we have to see that like in a class also, like I've given you between teacher and students, we have to see that we should not give the problem which is very complicated. So if the problem, any topic which is very tough to understand, it will be not easy to understand by the students and they will fail. They will not learn. Same way here, when we go for unsupervised classification, we have to choose the algorithms which are very simple to work. So here we don't have any freedom that any large number of algorithms we can use. We have to be very selective. So here you can see we can use the C-means or K-means algorithm, which is very simple algorithm. It uses only mean parameter. So using this algorithm, we can use this algorithm as unsupervised. If we come to supervised classification under this pixel-based parametric classifier, so we can have 3 or 4 algorithms. One is minimum distance classifier. This one is same, which I talked here. Only thing, this will work as supervised classification. Supervised means like in a school, in a class, there is a teacher to teach and the student learns through teacher. Like now it is going on. You are trying to learn through me on this topic. Second one, Mahalanobis distance. So there is a small difference between both. So here it use only mean, M. It is using only mean, but this one use mean as well as variance, covariance. So this one, Mahalanobis is an Indian name. It is a Bengali person from East province of India, from West Bengal. So he has given one distance called variance covariance. So that distance name has given on his from his surname called Mahalanobis distance or Mahalanobis classifier. The third one, parallelepiped or box classifier, and the fourth one under supervised is maximum likelihood classification. So there are 4 algorithms which I will cover under supervised classification algorithm. Then we will see classification accuracy. So if I talk about unsupervised, we have just image whatever bands it is 3 band or 5 band. We just apply the algorithm iterate and it generates clusters. So these are called cluster. It is not classification. For unsupervised, in the literature we talk about clusters. So these are your clusters. The difference is the label is missing. So there is no label, no name. I do not know what is green and what is red. So label is missing here. All right, I do not know red is water or agriculture. So label is missing. So it will get here C1, C2, C3, like that the class label will come. But later on we can give the label while verifying from the ground information. So here this is the unsupervised case for Euclidean distance, which is using only mean. So how it works, suppose these are the two clusters, it assumes, so we know we have to divide the data into two classes or two clusters. So to start the algorithm, it will ask C how many clusters you want. So I say 2. So it will assume the mean of cluster 1 and mean of cluster 2. It will assume, right? And this pixel has to be labeled, for example. So what it will do, it will calculate the distance here. Distance 1 is mod of xi minus x1, and then d12 will be xi minus x2. So like this, it will get two distances for this pixel, and whichever is minimum. So this is the unknown pixel here, xi, and this is the mean of cluster 1, x1, and this is the mean for cluster 2, x2. So it will find out these two distances, whichever is minimum, this will be labeled to that class. Suppose this is minimum to this, so it will be labeled as B. B is the cluster B. So like that, it will go on looking each pixel, and that pixel will be labeled to A or B. So after first iteration, what will happen? Few pixels will come here and few pixels will come here. So whatever pixels we got here, using these pixels we can find out new mean x1 and x2 dash. So we can find out the new means. So using new means, again we can calculate these distances for all the pixels one by one, and again we can get few pixels in this one and few pixels on this one, again using the minimum criteria, minimum distance criteria. So once we get few pixels in cluster 1 and few pixels in cluster 2, then using the new pixels, again we can find out mean of cluster 1 and cluster 2. So like this, it will go on doing iteration, and we have to define how many iterations we want to do. Suppose 10. So algorithm will do 10 iteration, but parallelly we can assign one more condition, epsilon. Epsilon is an error, right? That is a shift of the mean, because mean is shifting. Initially mean was here, then mean may come here, then mean may come here, and same way this mean is shifting. It was initially here, and then here. So this shift and this shift we can find out and take the average of both, and this is your epsilon naught. So here this should be less than or equal to. So any of these two conditions which are true, we can stop and algorithm will not process further. So like that, in a given image, it will divide the data into different clusters. Suppose it is two clusters, so like that we can get cluster 1 and cluster 2 as an output. So this is your unsupervised, and here you can notice that we have used the equilibrium distance, which is very simple algorithm as C-means algorithm, because it requires only mean parameter. So this here in unsupervised mode algorithm is using very simplest parameter, that is mean. Next is for supervised case. In supervised image classification, if this the image has to be classified, so from image we are giving samples for A class, for B class and C class. A is water, B is agriculture, and C is rock. So once we apply the signatures here for each class, so using the signature files, the algorithm calculates a mean of each class x1, x2, x3. So once we have mean, we can go for classification, and we can apply any of the 4 algorithms which I told you. So we can see here the 4 algorithms here: minimum distance, Mahalanobis distance, parallelepiped, and maximum likelihood. So what is happening in the minimum distance? I've told you the D has to be calculated like this: xi minus x1. So this is the mean, and mean for class 1. Once we have training data or sample data of class 1, we can find out the mean vector, mean sample or mean parameter of class 1, and like this for other class also. So we can find out this. So we can find out distance. Suppose this is the feature space. So mean, this is the first mean for class 1. This is mean for class 2. So this is a pixel we have to classify. So we can find out here distance 1 and here distance 2. So whichever is minimum, we can label this pixel to class 1 or class 2. So we can label this pixel to class 1 or class 2. There is heavy lightning is going on outside, so you can listen the sound of that also. Anyway, we'll come back. So here, like this, it is using only the mean parameter, and the minimum means the distance should be minimum. If you talk about Mahalanobis, the distance will come something different. It will be like this. I can write here. D will be xi minus x1. T is the transpose A inverse xi minus x1. So here this is the unknown pixel, this is the mean of that sample of a class, and this is the variance covariance matrix, inverse of variance covariance matrix, and you have to make under root also. Now from this you can find out the distance through Mahalanobis classifier, and once you get the distance, and you can find out the distance is smaller to 1 or 2. If it is smallest to 1, so you can label this pixel as 1. So you can label this pixel as 1. Like this, all the pixels are labeled. Here we don't have to do number of iterations. In single iteration, we can label all the pixels because we have training data, and we can calculate here mean as well as variance covariance matrix when we are using this distance. In this distance, we have to require mean and variance covariance matrix to be calculated. Plus, since we have training data, so with the training data we have the label. We have the label of the class. So we have label of the class. So in the same iteration, for each pixel, we can see the label. That pixel belongs to which class. The third one is your parallelepiped. So here what happens, it creates the box. So if this is your feature space, how it will create the box from the training sample. We have to calculate any of the parameter. We can calculate minimum and maximum. So this is A, suppose, and this is B. On each band, we can find out minimum and maximum. So here, this is minimum and this is maximum, A and B. Then here, it is your C and D. So again, for the band 2, we can find out C as minimum and D as maximum. So using these lines, if you extend, so you can make a box. So this box is, say, for class water. Like this, if you take the sample of class agriculture, you can create one more box for agriculture with a minimum and maximum concept. If the algorithms is using minimum maximum, the second method is you can use the mean and standard deviation. So using these mean and standard deviation, again you can create the box. So mean will come here. This is minus sigma, and this will be plus sigma. So on the both bands, you can create the box with respect to plus minus sigma and x. So then you can create the box. So any of this parameter we can use, and we can create a box. So now we can find out which pixels are lying in this box. The pixels in this box will be labeled to class water. The pixels in this box will be labeled to agriculture. So like this, the labeling is done, and the pixels which does not belong to any of the box, they will be labeled as unclassified pixel. Unclassified means these pixels does not belong to any class. So this way the parallel pipe classifier works. And fourth one is maximum likelihood classifier. Are you able to understand? Please let me know before I move further. Please let me know, are you able to get, or some issues, please type in the chat box. From Zambia, Kenya, is it okay? Mauritius, Bangladesh, somebody from India also? Rima Sinam, Bahrain, oh nice, okay, good, you understand. Mauritius, yes, it is okay, sir, good. Malika Rosie, Rima's Sinan, and then Moses from Zambia, okay, then it's fine. So let me cover the fourth one. Fourth one which was there here is maximum likelihood classification. It is called in short MLC classifier. This classifier use the probability. So probability formula I can write here. P probability will be 1 upon 2 pi to the power n by 2 mod of A inverse then e to the power minus 0.5 xi x bar to the power t, that is transpose A inverse xi minus x bar. So here n is your bands in the image, right? A inverse is your variance covariance matrix. Xi is your already told unknown pixel. And x bar is mean. X bar is mean, right? So here P is the probability. Okay. So if we take the feature space and we have training data of each class, so we can find out here mean of each class. We can find out variance, covariance. So with these two, we can find out probability P. So if this is a cluster 1 or class 1, and this is your class 2, and this is the pixel has to be classified. So we can find out P1 for class 1 and P2 for class 2 using this formula. Using this formula, we can find out, right? Here everything is known because it is supervised. So with the help of in the case of supervised, we have a training data. With the help of training data, we can find out these parameters for class 1 as well as for class 2. So once we do this, we can find out P1 and P2. Then we can find out which is greater. P1 is greater. This is maximum. Or P2 is maximum. If P2 is maximum, this will be labeled as class 2. So class 2 can be say agriculture. So 1 is your water and 2 is your agriculture. So like that, this pixel is labeled to class 2. If we find out one more pixel here and find out here P1 here and P2 here, if here P1 is maximum, so this will be labeled as class 1 and class 1 is your water. So like that, in single iteration, we can label all the pixels because it is working as a supervised algorithm. Why MLC cannot work unsupervised? Because it is using two parameters here, variance covariance and mean. Mean is easy to define or to estimate with respect to iterations, but it may not be possible to estimate variance covariance variable. So that's why it can work very easily for supervised mode, but not unsupervised mode, right? Next one, we have, once we get the classified map, the question comes, what is the accuracy of my map? So there are standard methods we can do to do the assessment of my classification output, that is confusion matrix. We can generate, this is also called error matrix, right? So what is required for this matrix? The required is, we require two maps. The first map is the reference map, which is having ground truth information about the classes. So this is the reference map. Second one, we require classified map. So there can be suppose classes like this, and here classes is like this. This is your water, forest, agriculture, water, forest, and agriculture. So since here there are three classes, so what we have to do, we require here 3 by 3 matrix. Water, forest, agriculture. Water, forest, agriculture. This side, it is classified data, and this side, reference data. So here we have to take some samples, testing samples. So here we have to take testing samples. Testing samples, we can follow some rules like Congleton 1991 told we should have 75 to 100 samples per class. So how this error matrix will be filled, and here you can see the matrix is this one, 3 by 3, the green boundary one. So this is your 3 by 3 matrix. So within this, we have to fill this matrix with values using the samples. So how we will do? If one sample is here and same sample is lying here, and in both the maps, I have lost the voice. Okay, from Thailand, from you can tell me where did you lost the voice. I can repeat, otherwise I will cover later. You can let me know. Is it okay? Fine. But during discussion, you can during questions you can ask me where did you left, so I will cover it again. No problem. Don't worry. I'm with you. Don't worry. Right? Don't worry. So here, one sample is lying here and on the classified. So here you see this is water on the reference map. Okay, thank you. Thai line. So on the reference it is water, and on the classified this is water. So here you say 1. So here you say 1. Then you take one more sample randomly. It is lying here and it is lying here. So this is agriculture on both. So here it is agriculture and here it is also agriculture. This will come here. Then third sample you take somewhere here. On the reference map it is water, and on the classified map this comes to be agriculture. So on the reference map this is water, and on the classified map this is agriculture. It will come here. Then you can take fourth sample, fourth one here, and here it is forest and forest, forest and forest. It come here. Fifth sample, if you take, it comes suppose here it is water, and here it comes as a forest. So on the reference map it is water, and on the classified map it is forest. It comes here. So like that you can generate for all the samples this complete matrix. So once it is full, then what we can do, like this, I have given you example. This is your matrix 3 by 3. So once this is done with respect to all the samples, then you find out this is your row total. And this side you have column total. So if you add this one, it comes 39, here 50, here 47, here 50, 40 and 46. Now we can find out some of the things like user accuracy. So user accuracy is the accuracy of the classified map. So here if you see, this is your classified map. Here you can find out user accuracy. The producer accuracy means accuracy of the reference map. That means how accurate your ground truth samples are. So user accuracy gives you accuracy of your classified map, and samples, how correctly they have been taken from the reference map, that accuracy you get from producer accuracy. So producer accuracy gives you the accuracy of your samples, how correctly they have been identified on the reference map. The user accuracy is basically gives you the accuracy, how correctly the samples are identified on the classified map. So here, if you talk about user accuracy, is the for class B. For class B, these are the samples correctly identified on the reference map, that is ground truth, as well as on the thematic map, that is classified image. So it is 37, and total samples here on the thematic map were 50. So 37 by 50 multiplied by 100, it is 74% accuracy. And parallel, you can get error of commission. So error of commission here will be 100 minus 74, then it comes 26%. Error of commission for class B. Now producer accuracy is basically how correctly the samples are for class B, again that is 37, and how correctly the total number of samples you have taken on the ground truth on the reference image for class B is 40. So it is 37 by 40, it is 93. And error of omission is again 100% minus 93, that is 7%. Then you can find out here overall accuracy. Overall accuracy, OA. So OA will be row total divided by total number of samples. That means correctly identified samples are this one for each class, and total samples are 136. So here you can find out 35 plus 37 and then plus 41 divided by 136 and then multiplied by 100. So this will be in percentage. So then you can calculate overall accuracy of your classified map. Fourth parameter is kappa coefficient. This kappa coefficient goes from 0 to 1. So this also you can calculate with respect to this formula. Here n is total number of samples. So this is your 136. XKK, it is summation XKK. Summation XKK is this one, summation 35 plus 37 plus 41. So here this will be 35 plus 37 plus 41, and this one, or at the bottom also, this is cross multiplication. This one will be, let me draw here, 39 into 50. 39 in, this is basically row and column total. So this is your row and this is your column total. So 39 into 50 plus 50 into 40 and again plus, it is now 47 into 46. So if you total up this, this will come here. N square is equal to 136 total number of samples and square it. So now if you put all these values, you will get kappa coefficient, and this will come between 0 to 1. This is not displayed in percentage, but this is small value 0 to 1. If it is around 0.8 or more than 0.8, it is very good. If it is 0.6 to 0.8, if it is 0.6 to 0.8, then it is good. This is very good. And if it is less than 0.6, it is a poor accuracy of the classified map. So this way you can do the interpretation, and using error matrix, you can generate the error matrix. So you can generate the error matrix from your map, and what is required? You require two maps. One is reference map, second is classified map. Okay, so these two reference map and classified map You can generate the error matrix using your testing samples. Once samples are used to generate the error matrix, you can find out row total here. You can find out column total. You can find out total number of samples. So if you sum up this one, or if you sum up this one, you will get 136 only, right? So from here you can get the user accuracy. With this you can find out error of commission, which is 100 minus user accuracy, which is basically accuracy of your samples on the map. Producer accuracy means accuracy of your samples on the classified on the reference map, and you can find out here error of omission, which is 100 minus producer accuracy. Then you can find out overall accuracy with respect to total number of samples correctly identified on the map plus total numbers of samples used, and then you can find out the kappa coefficient, which is 0 to 1 from this formula. And that's all for today's lecture. It is around 5 o'clock.